All right, today we are going to unlock one of the most beautiful and, frankly, powerful secrets of the electric field. It's a concept that lets us peek into this invisible world of charges using just a little bit of geometry and, well, a whole lot of genius. So let's kick things off with a puzzle. Imagine I hand you a totally sealed box. You can't open it, you can't shake it, you can't even weigh it. How could you possibly figure out what's inside? I mean, it sounds impossible, right? But in the world of physics, there's a surprisingly clever way to do just that. Let's just pretend for a second that whatever is inside that box is constantly sending out these invisible rays in every direction. Now, if you could stand outside the box and count every single ray that pokes through its surface, the top, the bottom, all six sides, that total count would tell you exactly how strong the source inside is. You know, more rays equals a stronger source. Simple as that. Now, this isn't just some fun little thought experiment. This idea, this concept of counting rays to figure out what's inside a closed surface, it's a fundamental law of our universe. And yeah, you guessed it, physicists have a name for it, Gauss's law. Here's the core idea in plain English. Those invisible rays we were talking about, that's what physicists call electric flux. Think of it as the electric field flowing through a surface. And the source inside our box, well, that's the electric charge. So Gauss's law just says that the total flow coming out of any closed surface tells you exactly how much charge is sealed up inside. And you know, like all truly profound ideas in physics, this whole thing can be summed up in one beautifully simple and elegant equation. Just look at that. The total flux, that Greek letter phi, equals the enclosed charge, Q, divided by a constant of nature, epsilon naught. That's it, seriously. That's the entire law right there. So let's quickly break this down. On the left, we've got phi. That's our total Frey count, the flux. On the right, Q is the total charge we've trapped inside our box. And that last symbol, epsilon naught, that's just a fundamental number that basically describes how electric fields like to travel through empty space. It's the key that makes the whole beautiful equation work. So why? Why does this work so perfectly? The reason is actually incredibly intuitive. It isn't magic, it is pure, beautiful geometry. To really get why, let's jump back to our thought experiment. Picture a single positive charge just sitting there, right at the exact center of a sphere. This charge is radiating its electric field outwards in all directions, kind of like a tiny little sun. Okay, now imagine we make that sphere bigger. What happens? Well, two things happen at the same time. First, the electric field at the surface gets weaker, right? Because you're farther away from the charge. But second, the surface area of the sphere itself gets bigger. And here is the absolutely incredible part. In our universe, these two effects are perfectly balanced. The field gets weaker in the exact same proportion that the area gets bigger. They just perfectly cancel each other out. And what's the result? The total flux, our ray count, stays exactly the same no matter how big or small the sphere is. This perfect cancellation is what leads to some truly amazing consequences. You could almost say it gives Gauss's law some incredible superpowers. Okay, superpower number one, and this is a big one. The shape of the surface doesn't matter at all. Because that total flux is conserved, you can warp that sphere into a cube or a pyramid or even some weird lumpy potato shape. As long as it's a closed surface and it encloses the same charge, the total flux passing through it will be identical. Q divided by epsilon naught every single time. And for superpower number two, the position of the charge inside doesn't matter either. You can push that charge all the way over into a corner, and the stronger field on one side and the weaker field on the other still perfectly balance out. The total flux doesn't change one bit. So the crucial takeaway here is this. The only things that can change the total flux are the amount of charge you've trapped inside and maybe the medium that it's in. The shape of your box, how big it is, where the charge is sitting inside, none of that stuff matters. It's an unbelievably powerful simplification. And one final really important rule, what if there are charges hanging around outside our closed surface? Well, they don't count. Any field line from an outside charge that enters the surface must also exit it. So for every line that goes in, a line comes out. The net effect is zero. That's why only the charges we've trapped inside our surface ever matter for the final count. So how do we actually use these superpowers? Well, by leaning on symmetry, we can solve problems that would otherwise require some incredibly messy and frankly awful calculations. Let's try out a classic puzzle. You've got a single charge. Q, and you place it at the exact perfect center of a cube. The question is, what is the electric flux passing through just one of the cube's 6 faces? Now, trying to solve this without Gauss's law would be a total nightmare of integrals, but with it, the solution is just beautiful. First, we know the total flux for the entire cube has to be Q divided by epsilon naught. Second, since everything is perfectly symmetrical, that total flux has to be shared equally across all 6 identical faces, which means the flux through just one face is simply 1/6 of the total. And there's our final answer. Look at that! We solved a complex physics problem with just simple logic. No calculus needed. That right there is the power and the pure elegance of using Gauss's law. But here's the thing. Gauss's law is so much more than just a clever shortcut for acing physics exams. It gives us this profound glimpse into the fundamental structure of our universe. When you really stop and think about it, this law is really a statement about symmetry. That perfect cancellation we saw between the field strength and the area, that's not a coincidence. It's a deep, fundamental rule about the geometry of the 3-dimensional space we live in. It's telling us that electric charge creates this conserved quantity, this electric flow or flux that spreads out into the universe. It's a property that is constant and dependable, and it's woven directly into the very fabric of space-time itself. And that leaves us with a fascinating final thought, doesn't it? If this one elegant symmetry governs the entire world of electricity, what other hidden rules, what other beautiful symmetries are out there, quietly shaping gravity, quantum mechanics, and the very nature of reality itself? Thanks for joining me.